Hello, everyone. I am Yaguchi from the Ethereum Foundation. Well, first, I'd like to say thank you to Techpoint and Ned. I remember when you first offered this opportunity to us, you said Techpoint would like to organize some Ethereum event too. And I thought, oh, that is interesting because this is where the foundation started. So we are excited to be here, and then again, as decentralized as our team and also our community are, this is our way to get together when we have a community event. So we are excited to be in this beautiful place. The weather is nice, and then I think compared to yesterday's event, this is more casual, very Ethereum-like community event, I believe. And I guarantee you will feel different vibes that the speakers talk. So I'm looking forward to hearing that, but also hope you enjoy the talks. Thank you very much.
I'm your MC for today. Next up, I'd like to introduce Vitalik Buterin. He is one of the kindest, funniest people I know, and he's going to be talking about transaction fee economics. But none of Vitalik's actions are transactional, and all of his love he gives away for fee. Thank you, thank you.
Yay, the crazy annoying music is over. Okay, so today I'm going to talk about a subject that's kind of a bit off the beaten path in that it doesn't tend to get as much media attention as some of the more flashy things like Casper and sharding and zero-knowledge proofs, but at the same time it is something that is very important to a well-functioning public blockchain and its ability to be efficient and be sustainable for the long term, which is transaction fee economics. Or why is the fee or gas price or rent so darn high? So, start off with the fundamentals, right? So, this is a blockchain. Blockchains contain blocks. Blocks contain transactions. Users, that is you, send transactions, and these transactions get included into blocks. Now, from an economic point of view, right, each transaction gives a private benefit to its sender. You send a transaction because you want to send a transaction, because you get something out of the transaction being sent and being successfully included into the blockchain. Whether you're making a payment to a merchant, or participating in some charity DAO, or sending your money into some on-chain roulette game, or whatever else you're trying to do. You personally think that you gain some value from a transaction, so you send the transaction, right? So that's the benefit of a transaction to the sender. Could be very different for each application, but it exists. The transaction also creates a private cost to the proposer that includes the transaction in the block. So right now, proposers are miners. In proof of stake, proposers are proof of stake validators. But in general, whoever decides what the composition of a block is the proposer. So in order for the proposer to take your transaction, package it up into a block, and publish a block, they pay some private cost. But this private cost is pretty much negligible, right? It's basically just a very tiny amount of computation, and it's pretty much free, and it's definitely vastly cheaper than the like 45 cents or whatever it is it costs to send a transaction on like Bitcoin or Ethereum or whatever public blockchain you're using. The much larger portion of the cost of a transaction is the social cost, and the social cost is an externality. It's paid by third parties that have no choice in the decision of whether or not this transaction gets included in the blockchain. So social cost into other nodes in the network. And this, first of all, includes every node that is downloading and processing the blockchain, right? Which includes proposers and validators. It also includes users. It includes regular individual people. It includes Etherscan. It includes exchanges. It includes pretty much everyone. Everyone who is fully downloading and processing the blockchain pays some cost because your transaction being in the blockchain makes their life ever so slightly more annoying. Now, ever so slightly more annoying multiplied by tens of thousands of people actually could come close to equaling 43 cents. This includes present users as well as future users that will be using Ethereum in 2019, 2025, maybe 2100. I have no idea if any of these systems will even be alive by then. So the social cost is an externality that is unaccounted for if proposers are the sole parties that are deciding what transactions get included. So if proposers are the only ones that decide, and they have full freedom to decide, then proposers are going to accept all of the transactions that are worth at least their private cost. But the social cost is much, much higher than the private cost. And so if proposers accept all of the transactions that they want, the blockchain will just have way, way more transactions in it than is optimal. And what will this mean? Well, you'll have nodes that take an extremely large amount of computational power to use. Chances are only 5 or 10 people will even be able to run a node, and a node will be storing a huge pile of junk, including an encrypted backup of each and every one of your hard drives. So we don't want that. So pricing of externalities, there's a long tradition in the literature of economics about pricing externalities. This is an economist whose last name is Pigou, whose first name I forgot, unfortunately, who came up with this notion of Pigouvian taxes, which basically means if you have something that people do that creates an externality, then you try to measure the price of that externality, and you charge people a tax which is equal to the social cost of their actions. So one of the main examples of this is carbon taxes. If you're polluting, a carbon tax would require you to pay for the cost that your pollution imposes, at the very least on the country that you're in, and possibly with international agreements onto the entire world as well. An alternative to carbon taxes is cap and trade, which basically means you issue a bunch of permits for polluting, and you restrict the quantity of them, and then people can trade the permits. Now, there was a paper by Martin Weizmann from 1974 that basically made this argument, right? Under perfect information, prices and quantity limits are equivalent, right? If you have perfect information about what all the costs are, you could set a price, or you could set a quantity limit and the market will set the price. And these two policies are kind of exactly identical to each other. Now, in reality, we don't live in a world of perfect information. We live in a world of very, very imperfect information. What is the social cost of including a transaction in a blockchain? Is it 43 cents? Is it 5 cents? Is it $8.98? We have no idea. We also have no idea how many people are willing to send transactions at some particular price. And we don't know, well, guess what? The protocol, which is a thing fixed in code that can only be possibly adjusted via a hard fork a couple of times a year at best, knows even less. So the really optimal policy is very rarely just either a price or a quantity limit, but depending on basically the way that the social cost curves and the social benefit curves look, the optima might end up being very different. Right? So the point that I'm trying to make here is basically that if you look at present-day blockchains, if you look at systems like Bitcoin or systems like Ethereum, Bitcoin Cash, all of these, they all use block size limits, but and they use block size limits in order to control social costs, right? They use them in order to prevent the block size from ballooning up to basically containing an encrypted backup of each and every one of your hard drives. And this a quantity limit is only one kind of policy tool that's available to control and properly incentivize and properly account for social costs and the incentive structure. And according to the economic literature, it's very often, in fact, almost always not the optimal tool in its pure form. So there is this kind of larger space of ways to incentivize correct transactions or transactions that should be included in the blockchain to be included in the blockchain, transactions that are not worth enough to their senders to be worth it to not be included in the blockchain. And there is this larger space of mechanisms that kind of should be considered and researched to a somewhat greater extent. Now, one question we can ask is, well, what is the social cost of including a transaction in the blockchain, right? Because ultimately the answer to this question is going to decide the answer to the bigger question of how big should the block size limit be? How big should the gas limit be? Should there be a limit? Should we instead get rid of the limit and instead have the protocol charge a fixed fee? Should we maybe have a fixed fee and a limit? So in order to answer this kind of question well, we need to look at not just the social cost at any one point, but the social cost across many different points. So a chart on the left is a study made by Cornell in 2014, and they basically tried to estimate if the size of blocks in the Bitcoin blockchain were to increase, how many nodes would continue to be able to process the blocks and stay synchronized to the network. If the block size were increased to 4 megabytes, the number of nodes would decrease to 90% of the original value. At 15 megabytes, it would decrease to 75%. At 38 megabytes, it would decrease to half. And at 211 megabytes, it would decrease to 10%. So this is one kind of social cost of shoving your transaction into a blockchain, right? The more transactions you shove, well, the harder it will be for people to run a node, and the fewer people you will have running a node. Now, this has two costs, right? One of them is that you get a cost because each and every computer in the network is incurring more of a cost. But you also have a second cost, which is as the number of nodes decreases, the network becomes less decentralized. It becomes more centralized, and this ends up incurring political risks, it ends up incurring economic risks, and all sorts of other issues, right? If the number of full nodes decreases to, say, somewhere between 10 and 50, well, you might have an idea of what the consequences are going to look like. This is one very crude measurement, right? If we assume that the utility, so kind of the cost of centralization is logarithmic in the number of nodes, which basically means that cutting down the number of nodes in the network by a factor of 2 always has the same cost. So it's just as harmful to go from 10,000 to 5,000 as it is to go from 1,000 to 500 or 100 to 50. Then the graph kind of looks like that, right? And so the drop in utility is basically logarithmic, right? So the first 4 megabytes in this little graph drops 0.15 points of utility, but then at the end, 211 megabytes only drop you about 3 points of utility, right? So the loss of utility actually starts off high, and it ends up kind of flattening out over time. And the intuition behind this basically, think of it this way, right? Imagine a blockchain where the blocks are empty, or the blocks, say, have 100 kilobytes in them. Well, with 100 kilobyte blocks, you can do a lot. You can shove a full node into every smartphone, you can shove a full node into every IoT device, you can shove a full node pretty much everywhere you want. Now imagine going from 100 kilobytes to 400 kilobytes. Chances are you'll lose a lot of that. Now imagine going from 1.1 megabytes to 1.4 megabytes. Sure, you lose something, but you don't lose as much, right? So this is kind of an intuition for why social cost of getting more transactions shoved into a blockchain might actually be sublinear. Well, this implies could imply a lot of interesting conclusions, such as there might potentially be multiple optimal block sizes, but this is only one way of looking at the problem, right? So here is another chart. This is the correlation between the amount of gas in Ethereum blocks and the Ethereum on-call rate. So the Ethereum on-call rate is basically a measure of kind of how poorly the Ethereum blockchain is handling the load, right? How long does it take to process the blocks, and what portion of blocks don't get processed in time to even become part of the main chain. And you can see that part of the graph is super linear, right? Part of the graph basically is, there's part of the graph that's kind of linear, and it goes up from 0.05 when the blocks are empty to about somewhere around 0.2 when the blocks become full. Another part goes up to about 0.4 when the blocks become full. Now, the problem is that as this on-call rate becomes higher and higher, the network becomes more and more attackable. The network becomes more vulnerable to 51% attacks, it becomes more vulnerable to selfish mining, nodes start dropping off, and when a node drops off, that node's hardware could potentially be bought up by attackers. So there's a lot of dangers that start popping up when the uncle rate goes really, really high. And really, there's no way at all for the Ethereum network to be able to stably process, say, a gas limit of 80 million instead of 8 million. So you could kind of argue that the social cost curve sort of looks like this, right? So on the left side, you've got your kind of high marginal cost initially, because there's, as you go from a very small blocks to small blocks, no more full nodes on every smartphone. In the middle, it kind of becomes linear, and then at the right end, it also starts ramping up, basically because as it ramps up, the risk of attacks goes higher and higher. So this is kind of one example of the kind of analysis, right, that can go into informing what block size limit and transaction fee rules might look like. Here is another issue, right, auction mechanisms. So here's how transaction fees currently work in most existing public blockchains. Basically, in economics, this is called a first price auction. Everyone submits a transaction. With their transaction, they submit a bid. In blockchain land, we call this a transaction fee. The auctioneer, who is the block proposer, possibly the miner, or whatever we call it, selects the highest bids, because that's how we maximize the revenue, and everyone pays what they bid. So basically, everyone sends their transactions, the highest ones get in, and if you get in, whatever you bid, you pay. The problem is there are mathematical reasons why this mechanism is not what game theorists call truthful, right? So basically what this means is that bidding optimally in this mechanism requires very complex strategies that know not just what your own value for a transaction is, but also what the state of the market is, how much other people are bidding, how much other people are likely to bid, what was the time since the last block, and a whole bunch of different variables that become very difficult to predict. So optimal strategy for users is extremely complex. And this leads to a lot of inefficiencies. So this is something that popped out of China very recently. Basically, this is a kind of professional geek squad, which is offering help to use, obviously paid help to users, and it's helping them to submit transactions with fees as low as possible, with a rate of success as high as possible. Right? So basically the idea is that there was this one service that seemed to use spamming the blockchain as a voting mechanism for which coins get listed on their exchange. And so lots of people are trying to spam the blockchain, and because of these gas inefficiencies, you get these third-party intermediary services that are basically helping people do this as efficiently as possible. Right? So on top of the inefficiencies of this stupid voting mechanism existing in the first place, you also have these extra inefficiencies that arise from people just having no idea how to set fees correctly. And as a result, professional teams come in to help. We could get rid of these problems with better mechanism design. So second price auctions are the alternative that economists often like pointing out. And the idea here is that everyone pays the same bid as the lowest bidder that got into a block. So the strategy for transaction senders becomes very simple. Step one, decide how much you value the transaction getting in. Step two, bid that amount. That's it. Now, why is this optimal? Well, there's basically two cases, right? The first case is that the lowest bid is higher than the bid that you submitted. If that's true, your transaction's not going to get in. But you're happy the transaction did not get in, because from your point of view, getting into the block at that particular point of time is a ripoff. It's too expensive for you. Second case, the lowest bid is lower than what you bid. And in that case, you do get in. Yay, and you're happy that you do get in because it was worth it for you to get in. And the exact value of your bid does not influence the price you pay. So there's a benefit here. The problem is, though, that even though the strategy for buyers becomes very simple, the strategy for miners becomes much more complex. Right? And the problem here is that this kind of mechanism becomes vulnerable to a manipulation strategy on the part of the proposer. So on the part of the entity that's creating the block. So what do, right? Basically, imagine you have a miner, and the miner is getting some transactions, and it's getting the bids, and that's kind of what the demand curve looks like. So you have some bids at lower gas prices, some bids at medium gas prices, some bids at higher gas prices. Well, what the miner could do is the miner could fill part of the block with fake transactions. They're just being sent from the miner to themselves, and that's the kind of darker rectangle on the right. And by doing that, the miner reduces the number of transactions from other people that they're accepting, but the miner also pushes the lowest bid price up. And so if you look at the size of the light gray rectangle, the miner's revenue, well, the x-axis shrinks a bit because the miner is rejecting transactions, but the y-axis becomes much bigger because the price goes higher. So basically, the miner has an incentive to participate in these kind of monopoly tactics. There are other even worse attacks. So for example, the miner might benefit from including their own transactions in blocks and pushing up the price of those. Their miner benefits from making private agreements with specific senders, where specific senders sends transactions with higher fees than their actual bids, and then the miner refunds them under the table. So there's lots of economic attacks that start to arise. Well, hybrid mechanism. So the idea here is that you basically establish a kind of minimum fee that gets burned. So the fee does not go to a miner, it does not go to anyone, it just gets basically deleted from the supply. Or possibly it gets kind of paid out as a block reward to the entire set of miners or validators over a very long period of time. And you adjust this fee so that on average blocks are 50% full. Right? So in protocol, you just have a mechanism that does this adjustment automatically. So in the normal case, what you do is you just check, is the minimum fee worth it? If it isn't, then you stay away. If it is, then you bid the minimum fee plus 1. And chances are you get included. Now, in the special case where suddenly there's a lot of activity all at once, well, it might get a bit chaotic for a while, but within a couple of blocks, the minimum fee can adjust upwards, and you can get easily included again, and it stabilizes. There's a more complex option, so you can allow transaction fees you can allow transaction senders to say things like, I bid the minimum fee plus X up to some maximum Y, starting from some block number. And the point of this is that it allows transaction senders to kind of express more complex opinions. Right? So here that allows expressing the opinion, I don't care when this transaction gets included, I just want it to get included, but I want to pay as low a price as possible. Right? So this clearly encodes what a lot of people's utility function. It clearly encodes the desires that a very large class of transaction senders have at some particular points in time. And it allows expressing this opinion and basically getting a fee as low as possible without having to hire some geek squad. So so that's another mechanism of how transaction fee markets could be optimized somewhat. Third issue here, storage fees, right? So basically the problem is that there's transactions in public blockchains consume different kinds of resources, right? So they consume bandwidth, because a block has to contain the transaction, everyone has to download a block, they download it over the internet costs money or people have limited bandwidth. Some people have lots of bandwidth, some people are sitting in a Starbucks or have a 250K roaming connection, various computational costs, and there is also storage consumption, right? So if, for example, you send money to a new account or you create a new smart contract, that is creating data that has to be stored. And it's creating data, and because smart contracts, at least in their current form, basically stick around forever, and accounts basically stick around forever, it's creating storage costs that must be incurred not just by the nodes that exist today, but also by all nodes that are processing the blockchain at any point for going forever into the future. So this is probably one of the major incentive misalignment issues in blockchains that exist today, right? You have this ability to fairly cheaply pay a one-time cost to create this object that has to be stored by people going forward forever. There's other issues too. So first of all, storage is underpriced. Second, transaction fees tend to be extremely volatile day to day, right? Some day the Ethereum gas price they can get you in is 1 gwei, some days it goes up to 100 gwei, some days it's in the middle. But the social cost of storage is not that volatile, right? The cost of everyone storing your file doesn't bounce up and down by a factor of 80 every week. Also, there's not enough incentive to clear storage. There's no incentive to clear storage earlier instead of clearing storage later. And there's incentive to create weird second layer markets like gas token. So there's a lot of inefficiencies in storage markets as they exist today. Right? So here's one possible solution: ongoing storage fees. So basically the idea is that instead of making storage be a one-time cost that has to be paid in gas, storage would be an ongoing cost that every single account would have to pay per block for denominated in Ether. for every single byte that it is storing. You have a smart contract, your smart contract's code and storage takes up 7 kilobytes. Well, you have to pay whatever the storage fee is times 7,000 every block. So what this basically does is it aligns incentives better because first of all, it means that if you store something that everyone has to keep, or if you publish something that everyone has to keep storing forever, then everyone has to keep paying for, or you have to keep paying for it forever. If you're not willing to keep paying for it at some point, then the object eventually gets deleted automatically when the account runs out of money and no one has topped up its storage fees. Now there's a trade-off. Like basically, is n a constant or can n change? If n is a constant, you have more fee predictability. If n can change, you can have more storage size predictability. So there's trade-offs very similar to the trade-offs that exist in kind of shorter term of blockchain inclusion markets. And this stuff can be studied. We can start looking at what the social cost is. Is the social cost more linear? Is the social cost less linear? What does the social cost curve look like? We don't. This is stuff we need to think about more, right? So this is, now ongoing storage fees have been a fairly controversial issue, and one of the reasons why is because they do make the developer experience more difficult in a bunch of ways. One of them is, for example, what if you build an application, and that application depends on some contract, and then that contract goes bankrupt because it didn't pay enough storage fees? What do you do? A lot of contracts written today allow anyone to perform some operation in that contract that increases that contract's storage size. In this kind of model, this would no longer work because the contract, basically that would allow other people to grief the contract by ballooning its storage size and causing its rents to go so high that no one will be able to afford it anymore. Third question, if there's some contract which is a public good that provides a little bit of value to a very large set of users, like a software library, who pays for its upkeep? So there are challenges. One interesting mitigation is hibernation. So basically, if a contract can't pay storage fees anymore, instead of being deleted permanently, it gets hibernated. It gets removed from the active state, and it gets put into the history. And it basically is just sitting there, and while it's in its hibernated form, no one can interact with it. But if you really want to interact with it, you can basically supply proofs and you can revive the contract, right? You can supply a pointer that says, here is the last time the contract was hibernated, here is what the contract's internal state was when it was hibernated. Then here is a proof that says the contract was not woken before, and now I'm going to wake it, and this sort of resets the contract to that particular state. So there is one kind of attack that you have to watch out for, where you basically kind of wake a contract twice in response, and the second time you wake it, you point to an older time that the contract went to sleep instead of a newer time, but there are ways to basically mitigate this kind of problem, right? So basically, this is another kind of modification that can be made to improve transaction fee markets. So there's still a lot of stuff here to kind of implement, think about in terms of what's the right way to implement these kinds of schemes, and there's still a lot of further research needed. But again, the point here is, right, that aside from the research into technical improvements like proof of stake, like scalability, and like privacy improvements as zero-knowledge proofs, there are a lot of these improvements that can be made on the economic layer in order to basically improve the blockchain's efficiency, make blockchains easier as a user, and basically by providing better incentives so that users stop imposing such large social costs on each other. And this is something that we have thought about a lot and really need to be thinking about more, and does deserve a lot of attention. So thank you.